Hello friends, in this video I'm going to explore the concept of memoization. So memoization is an optimization technique which is used uh, to speed up the computer programs by storing the results of expensive function calls and returning the cache result when the same inputs occur again. So the caching mechanism that which is described here is not the same caching mechanism that you might which are used in CPUs, right? So that in CPUs the caches are used based on the assumptions that the certain values which are used now are likely to be used again in near future. Okay, so but here we know for certain that certain function calls will be used will definitely be used. Okay, so such values of the function calls only we will be storing in a data structure. So in a data structure, and it can be queried in our program. Okay, so this technique is primarily used with recursion. So recursion is a powerful technique, right? And it can be used to solve from very simple algorithms to very complex algorithms. And due to the advancement of multi-core computers and parallel computing, uh, I should say that the interest in recursive algorithms are steadily increasing. Okay, so in our example, we'll be uh, we'll be looking at different ways of implementing Fibonacci series. So as given here, a Fibonacci series is simply okay. Wait, what am I doing? Okay. So a Fibonacci series is simply as is defined as, right? So the nth element in the sequence is can be computed using the sum of n minus 1th element and n minus 2th element. So for the base case, we can say that f of 0 and f of 1 are both 1. Okay. So how do we compute this value? So we can simply code using basic as defined here in a program by making recursive calls, okay, without any optimization, right? So this is how it will look like, right, in a very simple version. Okay, so we can implement Fibonacci series in a recursive way. Okay, so in a recursive way like this. So if n is less than or equal to 1, just return the value of 1. Else we compute the sum of two recursive calls, right? Two function calls. Okay, so this is how we can visualize the complexity or how many times the function calls will be executed. Okay, so this is the first function call. This is the root, right? The root function call. So it will fork two more functions calls, one with n minus 1 and another with n minus 2, and n minus 1 will fork two functions calls, one with n minus 1 and another with one with n minus 3. Similarly, the n minus 2 will also do the same. It will fork two more function calls. So as one might observe, certain function calls are repeated. Okay, and here we have not done any optimization to prevent the repeated function calls, which are obviously going to return the same value, right? Okay, so there is potential for optimization, and that's what we are going to see here, right? But in general, when the program executes, how it will execute is that, so at the root will fork a function called n minus 1, right? First it will fork this function call, right? And this n minus 1 will fork this function called n minus 2. So at any instant of time, you can visualize a path from the root node to the leaf node. So that's how the stack frame of function calls will execute, right? So I mean, what I'm saying is that the complete tree will not be taking up all the space in your memory at any instant of time. Okay, so the space complexity will be still, in this case, it will still be order of n. Okay, So in this case, space complexity is still order of n, right? It is not order of 2n. So time complexity, if we can solve this recursive equation, one might say that it is approximately order of, I mean, it is order of 2 to the power n. Okay, I'm not going to explain all these concepts, right? It might be done in another video, or it will never be done. Okay, so yes, let's visualize it with a simple calculation, right? So we are going to calculate the f of the Fibonacci series of 5. Okay, so 5 will fork a function called 4, and 3. 4 will fork a function called 3, and 2. 3 will 2, 1, 1, 0. Okay, so here it will 0, and as you can see, this subtree will be duplicated here again. Okay, and this is not good, right? So we need to optimize it. Okay, so what we do is that we okay, so before actually executing all the function calls, we create a data structure, right? We create an array of size 5 in our case. So let's name that array as cache. Okay, so we create the array of size 5. Okay, so no, size 5 plus 1 6, right? Because we are computing from f of 0 to 5, so there are 6 elements, right? So 1 to 5 there are 5 elements, and 0 to 6 elements. So you create a cache with 6 elements. So you initialize the cache with cache of 0 as 1, and cache of 1 is also initialized to 1, right? So we compute the recursive call. Okay, so let's assume that 5 forks 2 recursive calls, 4 and 3. So this is a sequential, this program execute sequentially. Okay, so only one leaf node will fork a call at any instant of time. Two leaf node cannot simultaneously fork a function call at the same time. Okay, so let's assume that the node 4 forks a function call. Let's say it forks a two function calls, 3 and 2. The same way, next only 3 will be allowed to fork a function call. Okay, so 3 forks a function call, 2 and 1. So 2 forks a function call, 1 and 0. Okay, so before actually executing the function call at each instant of time, we will check whether there exists a valid value in cache. Okay, so how do we know that whether a valid value exists in cache? So it's up to us to make sure that initially, let's say for the remaining elements from 2 to 5, the cache is initialized to some invalid number. Let's say that invalid number is 0. So initially, for cache of I is equal to 0 for all I belongs to 2 comma 3 comma 4 comma 5. Okay, no simple example. So 0 is an invalid number. So if it is an invalid, if the cache with respect to the particular number is invalid, we will continue with the recursive call. Else we will return the value from which is stored in the cache. Okay, so initially 4, there will be the cache of 4 will be 0. So 4 will fork 2 more calls. Cache of 3 will also be 0. So 3 will fork 2 more calls. And cache of 2 will also be 0. And 2 will fork 2 more calls. So cache of 1 and 0 will be valid, right? So they will return the value of 1. So cache of 2 will hold the value of 2. Okay. So cache of 3 can compute the value. Then cache of 3 will be Okay, so basically cache of 3, we will store the value in cache of 3 as 2 plus 1, right? 2 is the value of cache of 2 and 1 is the value of cache of 1. Okay, in this similarly, we compute the corresponding value for cache of 4. Okay, so now here is the fun thing, right? So initially, 5 forks a 2 function called 4 and 3. Okay, so in the function call with respect to 3, cache of 3 now holds a valid value of 3, which is computed in this function call. Okay, so this function call, I mean this subtree, actually computed the value for cache of 3. So no more function calls are forked. Okay, so it just returns the value. As you can observe, right? So only exactly 5 function calls are made. So 2, 3, 4, 5, I mean 1, 2, 3, 4, and this one will be 5th function call, let's say, right? So the time complexity in this case, it will be order of n. So we avoided repeated calculations of functions, right? I mean, we avoided repeated function calls. Okay. So let's see how it will look in the code, right? So fibmem, this is the memoized version of the function I have written here, right? So I have attached the link to the code in my GitHub in the description, so you can get it. And there's nothing much in this code. It's very easy to read. Let's say. So as I have explained, if the cache value for particular n is not equal to 0, means it has a valid value, right? So we don't actually fork much function calls. We'll just return that value, right? If it is not, we will fork function calls and store the corresponding value in the particular cache, right? The particular entry in the cache. Then we will return the value. So in this way, repeated function calls can be avoided. Okay. So this init function, it just initializes the cache. As you can see, 0 and 1 are initialized to 1, and all the other elements are initialized to 0, which is considered an invalid value in our program. Okay. So Fibonacci computing Fibonacci series dynamic programming is explained here. You can read it if you want. Okay. And let's see how it executes. How we can I have written the code in such so that we can observe the time taken to compute each function calls. Okay, so dynamic programming avoids recursion. We can compute the value of like the Fibonacci series at any sequence n. We can compute it in order of n time in a single loop, right? So one might assume that dynamic programming will always be much more efficient than memoization, but that's not actually true. But one drawback with respect to memoization is that we have a additional data structure of like say additional space complexity of order n, right? We have a array of size n plus 1 in this case. Okay, and we similarly we create an array of size n plus 1 in dynamic programming also, right? But memoization, it uses recursion, so we have to consider the stack frames allocated to recursive function calls. Okay, so here the actual space complexity is 2 times n. So memoization will take much more space, than dynamic programming. But with respect to time, they are almost similar, right? So let me compile this code. Okay, so here we are finding the Fibonacci series at the 30th Fib of 30. The recursion, it takes a huge amount of time. So, but both memoization and dynamic programming takes a same amount of time. Okay, if we change this number 30 to 50, okay, we will note some funny things, right? It will actually, the computation will actually go forever. So 2 to the power 50, you can think, see, 2 to the power 10 is approximately 1000. Okay, so if you are talking about 2 to the power 50, it is 10 to the power 15, and it is quite a large number, and recursion will take huge amount of time, and it's not likely. Okay, and the program is not like, it is not likely, it will not terminate, so I have to kill it. Okay. But let's see, and fib of 50 might be a very big number. Okay, so I'm just going to comment out the call to recursive function, and let's just execute it again. Okay, so as you can see, both memoization and dynamic programming completed in time. Okay, but memoization takes quite a bit longer to complete than dynamic programming. Let's see if it is the case. If I do it again, yes. Okay, so it actually takes a quite a bit amount of time, which is greater than dynamic programming, and this has to be explained with respect to the additional space that memoization takes. Okay, so I mean, cache misses could cause this problem, likely, right? But it is not that bad, because as we have seen, fib of 30, I mean, if we try to compute the Fibonacci series for value 30 using recursive call, the time taken is huge, right? But memoization for 50 itself, it works pretty fast. Okay, but as you can see, it is not as fast as dynamic programming, but still there is much more power to the expressive nature of recursion. Okay, so why recursion, right? So this is a famous quote, which in computer science: to iterate is human, but to recurse is divine, right? There are many reasons to it. Actually, this is a very simple program, so you might not realize it, but many complex algorithms can be expressed very easily in recursion. So if you try to look at the implementation without recursion, it is not likely that you are going to understand it very easily as you read it for the first time. But most recursive programs are much more easier to read, test, and understand. Why for testing it is easier? Because uh, you use a lot less variables when you in recursion. Okay, why? Okay, because of the recursive function calls. Okay, so each function call, you get a localized view of variables, right? So you don't need to explicitly specify more variables in your code. Okay, this might be a little bit advanced topic, but we'll see. I will expand on this concept later also. Okay, so let me give you some examples, right? So if you want to compute the maximum of an array of elements, let's say sequence of elements, okay? So A1, A2 up to AN, right? So this can be simplified as maximum of a1 comma maximum of a2 to an. Okay, so you can actually code it in this way. Okay, and you define maximum of a single element, let's say in this case an is equal to an. So maximum of empty sequence is actually not defined, right? It should throw an error. Okay, ideally maximum of an empty sequence should throw an error. All right, so as you can see, with recursion you can actually express finding the maximum of an array very easily without, and I have not specified any additional variables, right? So if you are using a loop, you are always going to use some variables, and it is likely that for variables to iterate through every element of an array. Okay, and it is likely that you're going to get into segmentation fault or something like that, right? So here you don't have to explicitly specify the local variable. All you have to do is make recursive function calls with some values. Okay, so this might be the reason why it would be much more easier to test a recursive algorithm than iterative one, than its iterative counterpart. Right? But this is a very simple example. A much more complicated example would be you are going to sort an array of n elements. Let me denote it in this way. This is the most compact way. Okay, you're going to sort an array of n elements. Okay. So how can you specify it, or you can do it in a simple way, right? I mean, you can with recursion you can express it in a very much more simpler way. First we will sort the first half of the elements, right? A1 up to a, let's say, ceiling of n by 2, right? One half we sort it here, then we'll sort the remaining half. We'll sort the remaining half from a n by 2 plus 1 up to a n. Then we will merge both these sorted sequence in a single sorted array. So this idea is employed in merge sort. So this function call and this function call can execute in parallel, right? This will produce a sorted sequence with respect to first half elements, and this will produce a sorted sequence with respect to second half of the elements, and these two can be done independently without any data races. Okay, and even this merging, it doesn't have to when we employ the parallel algorithm, it does not need to happen in order of n time. One can execute the merging part using binary search also, and this will make a new video. I have actually implemented this algorithm. Okay, but if you try to sort, okay, that one challenge will be try to sort bubble sort in parallel. Okay, try to sort bubble sort in parallel, and I can pretty much guarantee that it's not so obvious, right? So if you try, even if you try to sort bubble sort in parallel, you have to use subdivide the problem into smaller halves, and you should then do it. Even that will not give you any performance benefits, I assume. Okay, whatever, right? But with respect to recursion, parallelizing is almost obvious. Okay, but let's take a look into a much more complicated problem, right? So you are given a array. Okay, you are given an array of n elements from array of elements from 1 to n, right? and you are supposed to count the number of inverse pairs. So what does an inverse pair means? So let's given an array of n elements. This will take forever. This should be another video. So basically, I'm trying to explain the inverse pairs problems, counting let's say the number of arrays with respect to n elements. What are the total number of possible arrays with n elements with the given specific number of inverse pairs, k number of inverse pairs. You could find these problems in coding challenges. Okay, but this video, it's already too long, I guess. So we'll finish it here. Please comment your suggestions for future videos. Till then, bye.